Let us now wrap up the content of this unit. We have started with an overview of closures for cohesion, and we have seen that a variety of physical phenomena lead to these cohesive effects. Liquid bridge forces are certainly the most important forces and always dominate the situation if they exist. Hence, closing these type of cohesion forces is absolutely important. Another aspect is roughness. It is often simply overlooked, but can have a huge effect, especially on the second most important type of cohesion forces, which are van der Waals type of cohesion forces. We have also briefly looked at electrostatic forces and have seen that the estimates for those forces are as good as the prediction of particle charge. Unfortunately, particle charge is still very hard to predict. This is due to a still multi-physics challenge that we must attack when predicting particle charge, because phenomena like turbocharging, so the charging due to collisions, or the uncharging via the ambient fluid, are very difficult to estimate. There is another detail that needs to be mentioned. We have only scratched on the surface of cohesion closures. If you look closer in literature, you will find that many other closure models exist. For example, the hysteretic elastic force model, documented by Luding, can be used to also induce cohesive effects. We have also focused a little bit more on liquid bridges. You have seen that the rupture distance depends on the liquid bridge amount, so the bridge volume. This leads to a variable cutoff over which the forces act. It's easy for you to understand already that in such a situation one has to be very careful when choosing the neighbor search grid, specifically the skin distance. Another topic that was discussed is the splitting of the resulting liquid bridge force into a capillary and viscous force component. For the viscous force, also the particle relative speed is important. We have also discussed the effects of roughness on liquid bridge forces. These effects are complex and we could not discuss all of them in greater detail. Next, we have also looked into rolling resistance. We have seen that the rolling trace can be obtained by integrating the relative angular velocity. This is nice because the angular velocities of the particles are anyhow computed with the DEM. If you want to go for the most physically correct model, we have to pick a so-called Class C torque closure for rolling resistance. The reason is that this closure also works in the quasi-static or slow flow regime. Unfortunately, we have to invest into additional memory per contact, but this is the only way to correctly picture these rolling resistance torques. If we want to make a compromise and we have flows in which particles are in motion, the Class A torque model is a good assumption. Last but not least, we have looked into closures for the drag force. Of course, it is essential to couple the DEM with computational fluid dynamics or CFD to provide an adequate estimate for the local fluid speed surrounding the particles. This then results into a so-called CFD DEM model. We have unfortunately no time in this unit anymore to discuss greater details. However, what is important is that you understand that the drag force is extremely sensitive to changes in the local particle volume fraction. Thus, the reconstruction of the local particle volume fraction at the particle location is important simply because it's an input to the drag closure. If we look into current literature, we find room for improvements. And one thing that we have not discussed but is important is so-called fluid mediated drag. This is the effect that the surrounding particles induce fluid motion that is then felt as drag force by the particle we are considering. Also, there is a huge variability of the drag correction function F in a dense suspension. Predicting this variability is still very challenging. With that, I would like to thank you. See you in the next unit.